so to start us off, basically going back to what we were thinking about last lesson, but molecular formula, structural formula, skeletal and displayed. What I want you to just come up with, okay, there's a molecule. It has the formula C6H14. Can you draw a skeletal and displayed formula for it? But also, are there any other versions of that molecule that you can draw? Put my question mark in there. Let's see what you come up with. Is there any other versions you can come up with? Is there any different ones that might have C6H14 as well? Yes?
So for the structural Isomers, I'm just wondering, how would you know how many to have a CH3 and then how many to have a CH2, and how do you decide the order? Because you're breaking it down into.
So when you're doing a structural formula, you need to basically write what is around each carbon atom. Yeah? So if it's at the end, it will be a CH3. If it is in the middle, it will be a CH2.
That makes sense.
Yeah? You have got a different one. Good. Different versions. But I like the way you've done like balls and sticks. That's quite interesting. But then you've got the isomers anyway, yeah?
Mm-hmm. Yeah, these ones I just drew skeletals with them.
That's perfectly fine. Okay. All right. So, by the looks of it, most of you are actually done with that. Okay. And I bet you've come up with. Just take this off. If you do a displayed formula of C6, 6H14. Like I said last lesson, it gets a bit boring drawing all of these H's in when we do displayed formula. That's why chemists get lazy. We don't really like displayed formula that much. Okay, if you do that skeletal, then should look like that. Okay, so it's 1, 2, 3, 4, 5, 6 carbon atoms. Okay, you have to be careful. Just make sure you're always counting. There's always a carbon at the end, and then there's always a carbon where the lines change direction. Okay, but did you come up with any different versions? Who wants to have a go? Ahmed is going to get up and he's going to draw one of the other ones.
I only drew one.
That's okay, it's fine.
Okay.
Cool, okay. Let's have a little check of that. Thank you, Ahmed. So, the skeletal formula, I just want to check how many carbons it's got. I'm pretty sure you're right, but we've got 1, 2, 3, 4, 5, 6. Okay, that does work. And this carbon here is quite interesting. It's not joined to any other hydrogens. It's only joined to carbons. Okay. Did anyone come up with a different version of that? Or anything that you could change? James, come. Okay, let's actually have a look at that. Looks like a little, like some kind of animal almost. It's okay, you can go and sit down. So, 1, 2, 3, 4, 5, 6. Okay, that's actually perfect. What I'll do, James, though, just where you've got the end bit there, maybe to make it a bit clearer, you had it kind of like that, yeah? And it doesn't seem to be, no, it doesn't seem to be the same as the other one.
Are you allowed to change the structure of how the carbon atoms are laid out? Like when each carbon atom has to be formed as hydrogen molecules. Like wouldn't this change the way it's laid out in the displayed formula?
Exactly, it would change the way it's laid out in the displayed formula. So this is one example of the displayed formula for C6H14. You could do the displayed formula for both of these as well, but it would look different from this one.
So it doesn't have to be like that.
Doesn't have to be that. That was why I asked the question, are there different versions of it? Okay. Is there any more? Are there any more that people have come up with? Go on, Lee. Do you want to draw? Oh, okay. Very quick. So again, I'll just take this one off so we can see that clearly. So we've got 1, 2, 3 carbon atoms, 4, 5, 6. Perfect, yeah, and it looks different from this, and it looks different from the one that I just rubbed off. Okay, that's pretty cool. And so now it's time for my title for the lesson. Okay, you already knew skeletal formula, structural formula, displayed formula. So what we're going on to today is isomerism. Okay, so we need a definition of that word. I think some of you already know. And what we've been doing here already is working out different isomers of C6H14 or hexane. Okay, we've worked out at least 4 different isomers of C6H14. Okay. So, let's define this word. Okay, so general definition for isomers. So isomers are molecules that have the same molecular formula, but the atoms have a different arrangement in space. Okay, that's a very general definition of isomers. And actually what we're going to come up with are, there's many kind of sub-branches of isomerism. What you've just looked at, and this is the first one we need to play with, are structural isomers. So with the structural isomer, they have the same molecular formula. That's going to be the same for all isomers, but they have a different displayed formula. When we display out all of the bonds, all of the joins, you can see that they are actually different. Okay. So just to give you an example of that, then simplest one I can do, 2 isomers. So there I have C4H10, that's, what's that one called? Oh, everyone's gone quiet. Butane. Thank you, Jemima. Yes. Okay, I can do an isomer of that. Here we go. So now I've got exactly the same. I've got C4H10, but the longest chain I've got is of 3 carbons, and then a little branch off the side. Okay, it's still got 4 carbons and 10 hydrogens, but it's got a different displayed formula. Okay, it would have a different name as well. Yes?
Yeah, I was going to ask what the name would be.
Okay, so the name of this, again, we will do a lesson on nomenclature, naming stuff, but the longest chain is 1, 2, 3, so it's propane, and it's got a branch that is just 1 long, so we call that methyl, that branch. So this is just called methyl propane. Okay. So that's butane, C4H10. This is methyl propane, C4H10. Okay. For the most part, with this kind of isomer, just with branching, chemically it would react pretty much the same.
And is it the same for the other ones coming up, or?
It's not the same for all isomers. Okay. But for these ones, simple isomers like this, then yes. Okay. The major difference you'll find between these two is in physical properties. They'd have different densities, melting points, boiling points, and so on. Okay. And you could probably think, if you go back to what you've been doing on topic 2 and intermolecular forces, you could probably even say why these have slightly different boiling points. Yeah, even though they have the same number of electrons. Yeah, it's about points of contact. Exactly. Okay, so it all does link back together in the end. What we're going to do now, time to have a bit of a play with our molymods. Okay, everyone loves molymods, don't they? No? Yeah? Of course you do. Making models. I got 6 sets for 4 tables. So try not to mix them up. I'm going to give you 2 sets. I'm going to give you 2. Oh, you've got got the organic teacher one. There you go. 2 sets there. Try not to mix them up. I'm going to be mean and give you guys only 1 set. I know. All right, guys. So what we're going to do with those molymods in a sec is to see how many different isomers we can make of some different molecules. Okay. First of all, before you start with just making random models, Celia, can we just make sure, okay, the sets are all slightly different, but the black ones with 4 holes should be your carbons, okay? All we're really worried about, okay, is joining those together at the moment with the single bonds, the shorter grey ones, okay? Each carbon should have 4 nice short bonds with it, okay? And then we'll add hydrogens on the white ones. All right? What I want us to do first is to see how many combinations we can make that have the formula nice and simple, C5H12. Okay, we'll come back in a minute, see how many you actually managed to make. What we've been working on for the last few minutes are examples of what we would call chain isomerism. Okay, chain isomerism, really where the chain is branched, not branched, branched in different positions, making our new isomers. So I've just drawn up C5H12 as a skeletal formula. I'm feeling lazy. Okay, that's the straight chain version of it. Okay, if I want to make a branched version of this, well, I need to make it shorter. For a start, it can only be 1 shorter, okay, for now. And then I'll put a branch on here. I'm pretty sure all of you did that version. Okay. Did anyone draw that one as well? This and this. Go on, Ahmed.
Aren't they like equal?
Exactly, that was going to be my point. Okay, these two are actually exactly the same. Okay, if you imagine, I can just rotate this one, and I'd be able to superimpose it there. They are exactly the same. They are the same isomer. So actually, there's only this version. Okay. Did anyone come up with something else? A couple of people did. Ahmed, go on, describe for me.
So it goes 1, 2, like, I'm not explaining. Like,
Do you want to come and draw it?
so it goes 1, 2. Sorry.
Okay.
I
Okay.
think that's how it looks.
That's an interesting one. Have a seat. I like this, and I like that you've done that. Great teaching point. This is actually exactly the same as this. Okay? It's got 1, 2, 3, 4, 5 carbons all in a straight chain. Okay? All you've done is slightly change the angles. Yeah? So it's actually exactly the same. You've got to be careful when you do things like this, particularly when you're thinking about branches, okay? You can't have a branch on the end of a molecule because that's just extending the chain, okay? So you might have drawn this like 1, 2, 3, 4, and you're like, all right, I'll have a branch at the end. But no, that's exactly the same as this, yeah? So there is still one more version out there though. Ziad? One that's almost like a plus sign. Yeah, exactly. Okay. It can be drawn at angles or even just exactly like a plus sign. So it goes like this, like that. Yeah. Was that what you were going to do, James? What were you going to do?
A T-shape.
A T-shape.
So it's 2 down instead of 1.
Ah, okay. I'm just going to draw that in a second. So this one has got 2 branches on it, okay, on opposite sides. You can see the longest possible chain I can make in any direction is 3. 1, 2, 3, 1, 2, 3, 1, 2, 3, yeah, okay, and then it's got 2 branches, no matter what. What you described is really interesting, James. Okay, that is a good isomer there. So you said a T shape, so like this, this, and then you do 2 down from the middle, yeah? I'll do it 2 up, it will look better. Like that, more or less, yeah? But, there's a big but in there. We've already done this one. It's exactly the same as this. Yeah? Even if I just rotate that around a little bit, you might see that those fit over there. All I need to do is just change the angles of the lines a little bit, and it would fit over it. Okay? So you've got to be really careful that they are actually isomers of each other. Thank you very much for pointing that one out. That is a great teaching point. So, there's actually only 3 real isomers of C5H12. With a straight chain, there's this one with a branch. So, this would be pentane. This we would call methylbutane. This one is called dimethylpropane. Okay? But, like I've already said before, we've got a whole lesson coming on naming. So I'm not going to worry about naming them right now or the exact rules. Okay? So don't, please, panic. Okay? But those are the isomers. So that's just chain isomerism. Breaking the chain up, putting it in different places. Okay? What we're going to go on to next, it's a good one, is what we would call position isomerism. I'll give it a definition in a few minutes, but oh yeah, what we're going to try this time, we're going to keep with that C5 chain, okay. This could get really interesting really quickly. Actually, we'll go down. Sorry. We'll go down to C4H9Cl. Okay? You can use the chlorine is the little green ball like this. Okay? So you just need one of those substituted in for your one of your hydrogens. Okay? What I want you to do with a chain of 4, and you can change the shape of the chain as well. Is that the right one? How many different versions of that can you make? Okay. Think about the name that I've given it, position isomerism. It's going to be about changing the position, mostly, of the chlorine atom. Okay. Bit of a challenge for you. This is a good one. See how many isomers we come up with. Let's actually have a look at what you managed to come up with for different isomers for C4H9Cl. Okay, I could do the first one. If I put in skeletal formula, so there's my 4 carbons. Okay, 1, 2, 3, 4. I can put a tiny little line here and join that to a Cl. Okay, that's one isomer. Yeah. What I hope you noticed is it doesn't really matter which part of this carbon it's joined to. Okay, the carbons themselves. If I take this one, because you've actually made that particular isomer that way round. Okay, they spin around, so it doesn't matter which one it goes on. Okay, so it's just that chlorine on the end, exactly like that. Yeah. How can I change that really quickly to make different isomers? Just do what? Well, if I do this, that's exactly the same. Okay, I can take the chlorine and switch it to the second one. Okay? Now that is subtly different. Yeah? What I've drawn there, or what I've made there, sorry. If I put in my 4 carbons again, 1, 2, 3, 4, is the chlorine there instead. Okay? What would happen if I moved the chlorine to here? Would that be a different isomer? It's the same as this one. It's the same as just... So there I've got that one. If I just flip it around, like that, it's exactly the same. And likewise, if I move the chlorine to here, it's exactly the same as this one. Okay? So there's 2 isomers like that with a straight chain, but with C4 I can also make a branch chain, can't I? Yeah? So I've got a branch chain like that. Now I've got different positions I can put the chlorine in. Okay? Where can I put it? Okay, so I could put it here. Do a little line in my CL there. Okay? So I could put it there. Could I also put it here and make an isomer? Not quite. Have a look. If I just change this one very quickly to be branched. Ooh. There we go. Branch it in the middle. That off. Drop that off. Okay. So, hopefully you can see. So that's the one. That's that one there with the chlorine just here. Okay, that's the isomer you've drawn there. If I start to flip this around, I can put it in that position or even in that position just by rotating things around a little bit. Okay, so be careful. There is one other isomer like this though. Where can I move the chlorine to make it different, James? I can attach it to the one in the center, exactly. Okay, if I swap that round, there we go. Okay, that's now the chlorine on the center carbon atom. So I draw it. If I'm doing skeletal, it would have to be drawn a bit like that. Okay, like a little tree with a chlorine growing out of it. It's not, no, because it's on the middle carbon. Okay, this one is at the end of the branches, and the end of all the branches are exactly the same. We all right, gals? Good. Okay. So 1, 2, 3, 4 different isomers where we can change the position and also the chain of C4. Okay, just with one chlorine atom. Okay, if we were going to go through again. Hopefully you're already starting to get a little bit of a push for next lesson and talking about names. But this one we would call, well, it's butane, and it's got a chloro there. We would call this 1-chloropropane. This one, 1-chlorobutane. I forgot about the 4 carbons. This one, what would we call it, do you think? 2-chlorobutane. Because it's on the second carbon atom. So we call it 2. Okay? Oh, this one would be, well, we need the name of that chain first, which was methylpropane. Okay? So we would call that 1-chloromethylpropane. Because it's attached to carbon atom number 1. Okay? Even if it's up there, it's still carbon atom number 1. The first one in the chain. This one would have to be 2-chloromethylpropane. Okay? But again, we've got a whole lesson coming on naming things. So you've got, from this lesson already, two types of isomerism. We've got chain isomerism, we've got position isomerism. Yeah? We're building up and actually slowly adding to our knowledge of organic chemistry just by playing around with models and stuff. Okay? One more thing, which is for smaller molecules is not particularly common, but there is what we would call functional group isomerism. So I'm just going to define that for you while we finish off. So, okay, so functional group isomerism, this type of isomerism is when a molecule has different functional groups, so different actual groups of atoms attached to the carbon chain, but it still has the same molecular formula. Okay, maybe we can have a little think. So, it is possible, it usually happens with bigger molecules, but there's a challenge for you. Okay, C3H6O. I'm not going to make you build a model of this, okay, but there is a way to arrange this so you have actual different groups, but exactly the same molecular formula. Okay, what you have to think about is just remember that carbon needs to have 4 bonds. Okay, oxygen has to have 2 bonds. Okay, it is completely possible to have double bonds between the carbons. It is also completely possible to have a double bond from a carbon to an oxygen. Okay, it's a little challenge. See if you can come up with some, well, at least 2 possible versions of this. Okay. I hope that's correct. C3H6O. So yeah, it is. Good. We'll come back. What we'll do is next lesson, I'll tell you exactly what the 2 isomers are. Okay?